Hello, good evening to today's weekly session, problem solving session. I hope I'm audible. Am I audible, Sangamitra?
Yes, you are audible.
Okay. So today's session we'll be covering the questions related to the week 12 lecture material, which is basically on the economics of water supply system and the pricing of how water as a commodity is priced. So this again is going to help you with the assignment problems of week 12.
Actually,
Yes. Yes, Sangamitra, did you say
the
anything?
lecture videos are provided.
Uh-huh.
In case of lecture videos of this week,
Okay.
I found some problem in sound system. So, in initial part of lecture 58 and 59, so
Mm-hmm.
that sound quality was not good enough. So it was difficult to listen to the words properly.
Okay. Why did you raise this problem in the discussion forum or anything? Oh, were you able to convey this to anybody? Discussion forum? In the discussion forum, Sangamitra? Hello? Hello, Sangamitra, am I audible? Okay. I don't No, I mean, Sangamitra, I'm not able to, although you're online, I'm not able to get any response from you. So I understand there's a video quality issue. I will try to convey it to the team. And in case there's something that needs to be communicated, I'll definitely try to communicate through the discussion forum because I don't know. I don't think so. There's any other way I can get in touch with you. But I'll definitely try to communicate with the team and see what the problem is and if anything can be done about it.
Okay, I think other students have not joined. Otherwise, they might have told also.
Okay, okay, we'll
Whatever
see.
I am facing, yes.
Okay, okay. Let me see, and if there's anything, I'll just convey it to the discussion forum or next week's class. Whatever the update is, I'll let you know.
Okay, thank you.
Okay. So the week 12 lectures is mainly covering the economics of water supply system and pricing of water as a commodity. So we'll just go into those questions. So the first question is the economic value of water is determined by what? Is it the willingness to pay for the water for a specific use or the willingness to pay any price for the basic minimum amount for survival or the recognition of water as a good economic commodity or is it all of the above? As usual, you can just type in your answers in the chat box. Okay, so let's go on to the solution part of it. So water, like any other product, is a commodity with some value attached to it. And the value of water, you can only say water is having a particular value when people are actually willing to pay for it. So we know that water is a very essential commodity. So irrespective of the use, we essentially require water for our survival. So people will do anything to get water. So they are always willing to pay for it. But again, this just just willingness to pay for water because it is that essential is not actually helping us in putting a price to the water as a commodity. So in order to price water, it is required that people are willing to pay for it for a particular use. If it is for irrigation, then how much amount of prices are people ready to pay for it? If it is for electricity, water is being used for electricity, now how much of value are people willing to uh, how much is are people willing to pay for water as a source of electricity is again what is meant by willingness to pay for water, and value of water is based on this willingness to pay for a particular use. So in this question, what they have asked, so again, the economic value of water can be determined not by simply the willingness of people to pay for it because it is an essential commodity, but willingness to pay for water for a specific use of water. So the answer for this question would be option A. Moving on to the next question. Now, like we discussed about economic value of water. So the total economic value of water can be categorized based on two conditions. One, its use value, and other is the non-use value. Now, use value means when we are using or when we are paying a price for the actual use of water for a particular purpose, like if you are paying water for drinking purpose or if you're paying water for irrigation purpose, then all these values are coming under the use value of economic value of water. Now, what is non-use value of water? Again, this is also a value attached to water as a commodity, but not for its direct use. But say, for example, if you are using or if you are valuing water for a future generation, there is a water body like a well. We want to conserve it, or we are attaching a huge value to that water body because we want to save it for the future generation. Then such values of when you attach such value to the water, such values are called the non-use values. We are not actually using that water body or that water for any purpose for ourselves, but then we want to save it for the future generation. Because of that, we are attaching a value to that water body. Then such uses are called non-use values. You can see under non-use values, there's two values called bequest value and altruist value. Bequest value is when you attach a value to water body so that we can preserve it for the future generation. This can be through many ways. Like suppose traditionally there's a water body that has been passed on from one generation to the other as a valuable water body. Say a well is there, we are attaching some sacred value to that, or we are attaching some traditional value to that, and that water body and the water in that is being passed on from one generation to another. Then such value attached to water is called the bequest value. Now, altruist value is again when you are attaching value for the production or distribution of water for again the benefit of others. It can be for the benefit of another community, or it can be for the benefit of the habitat. Say there's a water body and you want to, the water body is valuable because it is helping the animals and birds in a place, or it is helping a particular community in a place. We are not using it, but we are attaching value to that water body because it is of benefit to others. Then such value attached to the water body is called the altruist value. Now, apart from use value and non-use value, there is another value called the option value. Option value is when water is seen as the opportunity, or there is a potential future scope for a water body that could be utilized in the future for a particular purpose, or a water body attached to a water body or a well or something is having a future potential use with that, then the value attached to it is called an option value. So option value can either be actual value, it can either be use value or non-use value. That depends upon what the future use is associated with the water body or the water as a commodity. So economic value in summary is categorized into two: use value and non-use value. Use value is when we the value of water for which we are actually using it, and non-use value is the value attached to the water for the benefit of others. It can be for future generations or benefit of anything else other than for our use. So, and option values when water has a potential future opportunity associated with this. So the next question is based on the different types of economic value of water. So an appropriate example of the non-use value of water is it drinking and industrial use, irrigation and other agricultural use, recreational amenities, or is it biodiversity conservation? What is an example of the non-use value of water is the question here. You can type in your answers. Correct, Sangamitra. The answer is biodiversity conservation. This is coming under the altruist value of water, which is a non-use value of water. Now, the option value of water is typically used to measure. We also studied about a third kind of value, which is the option use, apart from use and non-use. So what is it associated with? Potential future use opportunities, regulative measures, fishery and aquaculture, or none of the above? Right answer, Sangamitra. It is potential future use opportunities is what is option value of water is. We look here this use value, non-use value. Under use value, there's actual value. Non-use value is philanthropic values, which is for the benefit of others. Option value is for potential future water use. Another thing to remember is this can either come under use value or non-use value. Now let us look at some of the components of the cost and value of water. Now, as you can see in the left side here, there are various types of costs of water: environmental externalities, economic externalities, opportunity cost, capital charges, O&M, that is operation and maintenance cost. Now, capital charges and operational maintenance cost is coming together, comes under a category called the full supply cost. Now, capital charges, we know what it is. Whatever amount we are investing for setting up an infrastructure that will help in producing, distribution, and everything, supply of water is called the capital charges. And operational maintenance charges is again, suppose we are setting up a network, distribution network for supplying water, then the costs incurred when we have to keep the system running, and the maintenance charges are coming under operational maintenance cost. So capital charges and operation maintenance costs come together come under a category called the full supply cost. Now, apart from that, you can see opportunity cost here. What is opportunity cost? Opportunity cost is nothing but, say, suppose we have a certain amount of water and a farmer wants to use it for irrigation. But if the water was not used for irrigation, what are the alternate uses of water that can be used? Say if that water can be used for recreation, or that water can be used for drinking purposes, then what is the cost that is related to this alternate use of that amount of water is called opportunity cost. Now, why are we finding this opportunity cost? Suppose some decision makers want to decide what is the best allocation of fund for a certain amount of water. Is it best if we allocate it for, say, someone is saying, I want this much amount of water. If the decision makers have to decide if pricing that water based on the requirement is good or bad, then what uses of water, like the alternative uses of water, what will be the cost associated with that also should be known. So those costs come under opportunity cost. Now, apart from that, there's another cost called the economic externalities. Now, economic externalities are the costs that is occurring as a result of economic issues related to the water that we are using. So suppose we are using a particular amount of water. Even if we are using that amount of water, say there is some other problems coming from that water, say that water is contaminated, and people are getting some kind of health issues, then the cost that is incurred in eradicating this health issue or treating this health issue, all that cost that is not involved in the usage of water, we are just paying for the amount of water that we're using. But if there's any other economic situations arising because we are using that water, the cost associated to such external reasons of using that water is called economic externality. It can be anything. Suppose if there's health related issues coming because of water, then the cost incurred in sorting out these health issues, or infrastructure costs. We are only paying for the amount of water that we are using. We might not be paying for the infrastructure that is set up for this providing this water. That is also an economic externality cost. So economic externality cost plus opportunity cost plus full supply cost is equal to full economic cost. All these costs together is coming under full economic cost. Now, apart from that, there are environmental externalities. So, environmental externalities are the cost incurred because of the production, consumption, and the distribution of water, the environmental impacts that is associated because we are producing or consuming or distributing water as a commodity. Say water is being used for irrigation purposes, and as a result of these irrigation purposes, there is water pollution occurring or some kind of pollution occurring in the soil. So in order to treat that pollution or to control that pollution, whatever cost is incurred, such costs are called environmental externalities costs. That is the cost associated as due to the environmental impacts of producing, consuming, distributing water are called environmental externalities. So all of these costs together is called the full cost. So in summary, the full supply cost is, there are 5 types of costs. First is the capital charges and operational maintenance cost, which together come under the full supply cost. Then there is the opportunity cost and the economic externalities, which all together, which is coming under full economic cost. Then environmental externalities plus this full economic cost will give us the full cost. So the next question is based on the cost components of full cost. Match the cost with the appropriate components. Supply cost is given, economic cost is given, full cost is given. Okay, so I'll go ahead with the solution. So we had learned about 5 types of costs. The full supply cost, which means capital charges and operational maintenance cost. The full economic cost, which is the Sec B option, that is including the capital charges, operational maintenance, opportunity cost, and economic externalities cost, B3. Then supply cost will be, of course, A2. Full cost is again environmental externalities plus the economic cost. So the option C is the correct answer. A2, B3, and C1. So this is one probable area from which questions can be asked in this portion. Moving on to the next question. Next question is based on the price elasticity of water demand. So any commodity, when the price of the commodity increases, generally there is a decline in the demand of the product. So the demand curve, like for any other commodity, the demand curve for water is also a downward sloping curve. That is, as the price of the price of the commodity increases, the requirement, the quantity of water demand will also reduce. Now, what is this price elasticity of water demand? Price elasticity of water demand is a parameter or an index to see how consumers are responding to changes in price. So mathematically, it is represented by the change in the demand, percentage change in the demand, that is dx by x, divided by the percentage change in the price. So what is the change in the demand? Divided by a percentage change in the demand divided by the percentage change in the price gives us the price elasticity, which is represented by epsilon. Now, if this epsilon value is less than 1, that is the absolute value of epsilon, not magnitude, the absolute value of epsilon is less than 1, it means the demand is inelastic. That is, for example, if the price change in the price of water is 25% increase. When water is increased, price of water is increased by 25%, but the change in demand is a reduction, that is 10% is only reducing in the demand, then the demand is less than the value of the increase in the price. So in that case, the epsilon value we get will be less than 1. The absolute value of the epsilon value we get will be less than 1. In such cases, we say that the price elasticity, the demand is inelastic. Now, if in the alternate case, if epsilon magnitude, absolute value of the epsilon value is greater than 1, this happens when they change, suppose the increase in the price is 25% increase. In that case, the demand is reducing by 50%. So the value of reduction in the demand is more than the value of the increase in percentage increase in the price. So in that case, we will get, when we are dividing 50 by 25, we are going to get 2. So 2 value is greater than 1. So epsilon, the price elasticity is said to be elastic, or the demand is said to be elastic. So this is how price elasticity is evaluated. So we know price elasticity is the percentage change in the demand by the percentage change in the price. This formula is important because there might be small numericals asked based on this. This is Px by x divided by dp by p, and also this relation, that is, if the absolute value of price elasticity is less than 1, it is inelastic, and greater than 1, it is elastic. So let's move to the next question. Here they've given the price elasticity of water in a city consuming 25 million liters per day is minus 0.63. That is, epsilon value is equal to minus 0.63. What is the percentage reduction in water consumption if the unit price of water is raised from 12 rupees to 15 rupees per kiloliter? So here they have given the change in the price. Price is increasing from 12 to 50. So we have the dp value. Now p value is the initial value, which is 12. So we have dp value, which we have p value. We also have the epsilon value. We also have the x value. What we are supposed to find? We are supposed to find the percentage reduction in water consumption. So by using this formula, you can find out dx by x by dp by p is equal to epsilon. You can find out what is the percentage reduction in the use of water. Sangamitra, you can give it a try, right?
Yes, I'm doing.
Okay.
That means P is 12 and DP is 3.
No, DP is equal to 15 minus 12. That is a
15
change.
minus 12. That is 3.
Okay, 3.
That is 3. And epsilon is 0.63.
Minus 0.63.
Minus. We have to consider that negative, or as it is
Yes,
reducing.
it is, yeah, this percentage reduction only will be there.
Yes, so we have to
Okay.
consider the magnitude only.
Yes, 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 yes.
0.63. And that 25 is, it is given
X.
Oh, that is X value.
Yeah.
Okay. That means we have to say dx by x, or
No,
only
there are
dx?
the percentage reduction in water consumption. You will have to find dx.
Only dx. Actually, dx by x is coming out as
No, percentage reduction, you're right. It will be dx by x.
dx by x. Then it is
You're right.
16%. I think B.
Okay.
15 point something, 15.75 around.
Okay. Let's see the answer. Yeah, you're right. So again, percentage reduction will be minus x percentage. Percentage change in price is 15 minus 12 into 100 divided by 12. The P value is 12. Change in price is 15 minus 12. So 25% is the change in price. Percentage change in price is 25%. Price elasticity is equal to percentage change in water consumption. That is percentage reduction in water consumption divided by percentage change in price, which is equal to minus 0.63. So X value will get it as 15.75, which is 16%. So since they have told that it is the percentage reduction in water consumption, you can consider dx by x as minus x. Okay, let's move on to the next question. If the percentage change in water demand in a city is larger than the percentage change in price, then what is the price elasticity? Is it negative? Is the demand considered inelastic? Is the demand considered elastic? Or is it none of the above? You can type in your answers in the chat box. This is for the new participant who has entered. Okay, correct. The answer is demand. We had seen if the percentage change in the sorry, change in the demand is less than the change in the price, then it is called inelastic. And if the epsilon value is greater than, but when the change in the demand is greater than the change in the price, then it is elastic. So the answer for this question would be the demand is considered elastic. Now, an effective mechanism to ensure or enhance the value of water in a modern economically driven society is, how can we make sure that the value of water is uh, fulfilled, or people give value of water in a modern economically driven society? Is it by taking ownership of giving ownership to the water services to people, Is it by regulating utility operators, people who are responsible for production and distribution of water, having a control over that, or is it by economically pricing water, or is it all of the above? You can take a guess, then we'll move on to the explanation. When do we have a value for a product? For any product will be valuable to us if we invest some money in it. So if you buy a product spending our own money, we'll have value for it. So in this way, is this one of the way to ensure people give importance to water, or is it if we have a regulation over the people who are operating the supply and monitoring of water? Is it through that way, or is it by giving an economic setting an economic price to water that people will start valuing water, or is it all of the above? So let's move to the explanation. So water, uh, we can ensure or enhance the value of water when people start owning water. So, like I said, if we have ownership over a product or a commodity, we will obviously start valuing the product because we have invested some amount in that product. So, one way of ensuring the water is given its proper value is by giving ownership to the people. Now, regulation. When you when we start controlling the supply and the production of water, or we have a regulation over people who are responsible for it, that will also make sure that there's some people value the water as a uh, give enough importance to water as a commodity. Also, if we ensure that water is properly priced, then also people will give an importance to water. So the answer for this question will be option D, all of the above, by giving ownership to the people, then setting a regulation for the utility operator, and proper economic pricing of water. All of the above will help ensure the value of water in a modern economically driven society. Moving to the next question. Before we move on to the next question, now when do we say economic a project or a project is economically feasible? Suppose when we invest an amount in a project, and if we are getting the profit that we are getting is more than, if we are getting profits or the benefits we are getting is more than whatever we invested in a project, then we say that the project is economically feasible. So water supply projects also, in order to ensure that the funds are allocated in such a way that the water supply projects are economically feasible, there are some techniques, capital budgeting techniques that can be followed to make sure that the water supply projects are economically feasible. The names of such capital budgeting techniques are benefit cost ratio, payback period, net present value, internal rate of return, etc. are some of the budgeting techniques that will help in allocating funds appropriately, so that whatever water supply project people are investing, or whatever water supply project is being invested on, turns out to be an economically feasible project. So these are some of the capital budgeting techniques that will help in allocating funds for an economically feasible project, or to evaluate the feasibility of the fund allocation: benefit cost ratio, payback period, net present value, internal rate of return. The next question is based on this. What is an appropriate capital budgeting technique to evaluate the fund allocation feasibility in water supply project? Is it the willingness to pay, cost benefit ratio, internal rate of return, or both, B and C? right? It's option D. So like once again, just moving on to the capital budgeting techniques followed. It is benefit cost ratio, payback period, net present value, internal rate of return are some capital budgeting techniques that is used to evaluate the feasibility of fund allocation for an economically feasible water supply project. So the answer will be option D, cost benefit ratio and internal rate of return. Now moving on to next part of the portion, which is water tariff model. So how do we price, or uh, how do we charge the consumers for money? So there are various tariff models that are used for charging water consumption from the users. So two major types are the flat rate models and the volumetric rate models. In flat rate model, the tariff model, one of the tariff models is the fixed charge or flat rate model. We'll just briefly go through what those models are. In volumetric rate model, it is a uniform volumetric tariff model, increasing block tariff model, volume differentiated tariff model, decreasing block tariff model, two parts tariffs, and seasonal tariff model. So there are majorly two types of models, flat rate models and volumetric rate models. Sorry. The flat rate model, one of the flat rate models is called the fixed charge of flat rate model. In volumetric rate models, there's uniform volumetric rate model, increasing block tariff model, decreasing block tariff model, volume differentiated tariff model, two-part tariff model, or seasonal tariff models. Now, fixed rate charge of flat rate model is a model where how much ever water is consumed per month, you're charged one amount. So the consumer has to pay a monthly water bill irrespective of the amount that is being charged. So the graph will look like this. How much ever is the water that is being consumed, how much of volume of water is consumed, the price that will have to pay is the same for everybody. So someone might use less, someone might use more, but irrespective of that, everybody will be charged a uniform, a constant value on a monthly basis. But how can we make this fair? Like some are using less, some are using more. So the charge is fixed based on certain criteria. And some of the criteria are the connection size or type, the consumer type. So if such a system is existing in a say a community which is highly paid people, the salaries of the people are more in such regions, this price of the monthly water bill might be more. Say if there is a community which is having a less paid salary, then the price of the water or the total price that is monthly water bill is going to be less. So this is how they implement this uniform, the flat rate model. This flat rate model again is based on the consumer class or consumer type, the connection size or type is what is actually uh, relevant to this flat rate model. And this is used when there's no metering system. We are not able to know what is the volume of water used because there's no metering connection. In such places only, these fixed charge of flat rate models are used. Now, the second type is volumetric tariff models. In volumetric tariff models, the first one was the uniform rate tariff model that we studied. So in uniform rate tariff model, there will be a meter. We'll be able to know the volume of water that is being used, and relating to that volume only the price will be there. So if you see the second graph here, as the consumption increases, the price also increases uniformly. So in this, for water is classified into certain units. That is, say water consumption is 1 meter cube, then there's 10 rupees assigned to it. 2 meter cube, then there is again 10 meter for the second meter cube of water, there's again 10 rupees assigned to it. So there's a uniform rate in the rate of uniform increase in the price of the water with the increase in the total water consumption. Such a model is called the uniform rate model. And obviously, we need to know the volume of water. So there will be a metering system over here. This is also called the constant volumetric tariff, uniform rate tariff or constant volumetric tariff. So the first model that we learned was the fixed charge of flat rate model. In this, there's no meter connection, and the condition of the criteria for charging the prices connection type or consumer class type or consumer type. In the uniform rate model or constant volumetric tariff model, the consumers are paying proportionally to the volume of water they are using. There will be a metering system, and the price of water charge is not based on the consumer class or customer type or connection type. It is based on the volume of water that is being used. Now, another volumetric tariff model is the increasing block tariff model. What happens is, suppose until 10 kiloliters of water, there's a price assigned. If the water consumption is, this is the kind of tariff system that is employed in our place and all. If for the first 10 kiloliters usage of water per unit, that is for 1 unit of water, it will be 10 rupees. Now, if the consumption of the water increases from 10 to 20 kiloliters, the per unit charge will increase subsequently. So blocks or slabs are being set for the water to be used. That is for 0 to 5 kiloliters of water per unit. That is one. If 0 to 5 kiloliters of water are only used, that is only 1 meter cube kiloliter of water is used, then you will have to pay 10 rupees per kiloliter. But if the consumption of water increases 5 kiloliters, say every month we are using 10 kiloliters of water, then for the excess amount of water that using per unit, you will have to pay an increased value. So you can remember this graph, the price and the price is increasing based on slabs of water consumption. This is also called the tiered pricing method. So here is a comparison of the schemes. The flat rate method, in flat rate method, water bill does not reflect the cost of the service, because again, one constant value is given for a particular month. So what the cost of the service, neither the cost of the volume that is being used is considered. But in every other case, the uniform volumetric rate, water bill is directly related to the water use. Even increasing block rate method also, water bill is directly related to the water use. Remaining every volumetric tariff models, water bill is related to the water use. It is only in the flat rate model that water bill is not related to the water use. And this flat rate model happens only when there's no metering system. Remaining models, there has to be a metering system. So the 10th question is based on this. In which of these water tariff models, water revenue is independent of the water use? So if you are joined late, you can type in your answers in the chat box. So what tariff model charges water not based on the water use? It is independent of the water use. Right. So it is a flat rate model, like we had seen. It's only the flat rate model that is independent of the water use. Remaining constant volumetric rate or uniform rate model, increasing block tariff model, and all is making use of the volume of water. So the option for this question is option B. Correct answer is option B, flat rate model. Now, if you look at the increasing block tariff model, like I said, for every unit of water, for every range of water that is being used, it is defined as a block of water. That is, if you can see, if water consumed is say from 0 to 5 kiloliters is one block, 5 to 10 kiloliters is one block, 10 to 20 kiloliters is one block. So what is the criteria, or what are these blocks of slabs of water called? So in progressive tariff structure for an increasing block tariff, if you can see, The first block is called the social or lifeline block. That is, that amount of water is essential for us. Minimum requirement for anybody is what is consumed in that block. So a social or lifeline block is when the volume corresponds to the essential minimum consumption of water. Now the second block will be a normal block. That is based on some cost. We have to use some extra water is being used, and extra water is being charged a marginal cost. This can or cannot, may or may not be used. Not everyone requires this water, but if that amount of water is required, it will be charged a basic amount of water. It is an average consumption for a average cost of water. The third or more than this normal block is called a high price block. This in this block, when you set the price of the service that is provided for the distribution of water, production, supply, all these service charges are also included in this cost, because that is one quantity of water that can be avoided. But in case if you want to use it, you will have to pay a very high price for that amount of water that you're using. So these are the three blocks of how water slab is set, how the blocks of increasing tariff block, how the water quantity or the pricing or the value attached to each block is in this way. First is the social or lifeline block, which is the essential minimum consumption of water. Second is a normal block, small amount or average consumption of water based on marginal cost. High price block, in this block, for whatever is consumed, this price charge will include all the service charges also. So the 11th question is based on this. The social or lifeline block in an increasing block tariff structure represents what? Okay, so the right answer is option A. Social or lifeline block is the volume of water corresponding to the essential minimum consumption. Average consumption defined on the basis of marginal cost is called the normal block. The price block designed to finance the full cost of the service is called the high priced block. So this is also one, the water tariff models is something maybe you can put your focus on in this chapter. Moving on to the next question. Now, there is another system. We learned about three systems. One is the flat rate model, one is the uniform rate model, one is the increasing block tariff model. There is also called a decreasing block tariff model. Now, decreasing block tariff is actually the opposite of increasing. If there, as the water consumption increases, the blocks are given for increased usage. In this, it's opposite. As the water consumption increases, the price is kept on reducing. Now, where will such a scenario arise? In large industrial areas, they'll have very high consumption of water. So in such a high consumption of water, what happens is this kind of tariff is set for people or industries or specific areas of usage of water that requires a lot of usage of water. And why they logically, when we say when you use high water, we have to charge a high price. But this is such a system is brought about so that it will encourage large industries or big industries or factories to come in certain place, because their water consumption will be high. So as the water usage increases, for the increased usage of water, there's a subsidy assigned to it. This is to attract large industries and all. This is not a very what to say, it's not a very good practice of assigning tariff. This is more of to improve the, what to say, large industry, the monetary benefits for that particular region. But when you see in terms of the water usage, the water will be excessively used, and the price that is for excessive usage, if the price is reduced, water conservation or the water as a valuable product will not be efficiently used if the price of water is decreased at a higher rate. So this is mainly to attract large industries and all. So this is called the decreasing block tariff. And as you can see, it is a disincentive for reducing wastage of water. A lot of water will be wasted because people are not bothered about the price, because as much as water you're using, the price is reducing. So there will be a lot of wastage of water because people are not people are not worried about the cost that will occur. So most of the places, such a decreasing block tariff, this was implemented for political purposes or for improving the economics of a place in terms of industries. But from the time water has been recognized as a very valuable resource, such a system of assigning pricing to water commodity has phased out. People are not making use of such water, such tariff scheme. Although there are in places in USA and Canada, there are decreasing block tariff systems still being practiced. So next question is this: efforts to phase out the decreasing block tariff method in several countries are primarily because. Is it because it penalizes the economically weaker sections of the society? Is it because it is too complicated to implement? Or is it because no cost incentive to reduce the water wastage? Right? It's option C. There's no cost signal or incentive to reduce water wastage. So this uh, system of uh, assigning tariff or pricing system called the decreasing block tariff is being phased out in most of the places. So question 13. Which of the following is not true regarding the constant volumetric tariff model? Constant volumetric tariff model is the second model that we learned. There are flat rate model, uniform rate model is also called as the constant volumetric rate tariff model, where there's a linearly increasing curve between the price and the consumption. So what is not true regarding this model? Is it all water units are priced the same independent of the use? Is it consumers pay proportionally to their water consumption? The unit price of water increase at a constant uniform rate within each consumer class, or consumers must have a meter installed for implementing the tariff model? Okay, move on to the answer. It is option C. In a unit constant volumetric rate, consumers pay proportionally to their water consumption. That is per unit. This graph is for price per unit. Water consumption in terms of meter cube, the price is total consumption, but there's no increasing blocks. The per unit charge is constant irrespective of the use, but as the water use increases, the total price that is being charged per consumer is increasing. One important factor here is there is no customer class or consumer class based on which this water tariffs are being assigned. That is for the flat rate model. So the answer for this is the unit price of option C. Unit price of water increases at a constant uniform rate. Now this is the data of an increasing block tariff structure. That is, 4 slabs are there. It is charged rupees 5 per kiloliter for the first slab. 0 to 5 kiloliters per month, rupees 5 is charged. 5 to 10 kiloliters per month, rupees 10 is charged. 10 to 15 kiloliters per month, rupees 15 is charged. And for more than 15 kiloliters per month, rupees 20 is charged. What is the monthly water bill for a household consuming 25 kiloliters of water in a month? Only 25 kiloliters are being used. How will be the money or the price assigned for each unit? How will you calculate the monthly water bill based on 25 kiloliters of water being used? I'll give you a few minutes to think about it and answer. So first, in such a problem, first what you have to do is you have to segregate the total water usage. That is 25 kiloliters is the amount of water that is being used per month. So in 25, for the first 5 kiloliters, it is rupees 5 that is being assigned. So you will have to multiply 5 into 5, and then for 10 kiloliters, again one extra 5 kiloliters of water you are using, the extra 5 amount will be charged 10 rupees. Then for the next 5 kiloliters, that is 15 kiloliters that you are using, it will be charged rupees 15. Then next whatever is remaining is only 10 kiloliters of water out of the 25 kiloliters water. For the next 10, it will be charged 10 to 15 rupees, 20 kiloliters, 20 rupees, and adding all those you will get rupees 350. And how did you get 500? Okay, so this is how the problem is done.
Actually 5 into 5 means for first 5 kiloliter of water.
Yes.
Then again for next 10 kiloliter of water, it is 5 into 10. Because
Yes.
totally
Yeah,
they have
so
used 25 kiloliter.
Yes.
So
this 5 which I am showing in my with the laser is the first 5 kiloliters of water used. If you stop with that, only 25 rupees will be charged. But then they are again using uh, extra 5 kiloliters. So totally there are 10 kiloliters of water used. The first 5 will be charged 5 rupees. The second 5 kiloliters of water will be charged 10 rupees. Now again they are using extra 5 kiloliters of water. So first 5 again will be charged according to first slab. Second 5 kiloliters is already charged according to second slab. Third 15 kiloliters of water is charged according to third slab, because 10 kiloliters of 15 kiloliters of water is being used. Now what is the remaining in the 25? It is 10 kiloliters. So the 10 kiloliters, the last 10 kiloliters will be charged according to the last slab, which is 20 rupees per kiloliter.
Yes, I understand.
Okay. So take care not to jump into the last this one. You have to segregate into the slabs. So 5 kiloliters. When cumulative is 10 kiloliters, then first 5 liters will be charged according to first slab. Next 5 kiloliters will be charged according to the second slab. If it is 15 kiloliters that is being used, the first 5 kiloliters will be charged according to first. Second 5 kiloliters will be charged according to second. Then the excess amount will be charged according to the third slab. So it has to go like that in an increasing way. So this is how this problem is done. You might want to look into the practice problems in the lectures also. They have, this is for increasing tariff method. There are problems for flat rate model and uniform or constant volumetric tariff also. So please do go through those problems. Now the 15th question. Cost of operation and maintenance of water supply system serving 50,000 households is rupees 45 lakhs. They are using a uniform tariff model to recover the entire operation and maintenance cost. If a household is consuming 15 meter cube in a month and is paying 120 rupees bill per month, what will be the tariff under a uniform tariff scheme? That is, what will be the rupees per meter cube of water that is being charged? Move on to the solution. So this is nothing but you can just divide by the monthly amount by the volume of water that is being used. For uniform tariff rate, the calculation is as simple as this. What is the monthly amount that you're paying divided by the volume? You will get rupees 8 per meter cube. Now, if you want, you can cross check this by multiplying 50,000 into 15 and then seeing what is the cost that is being incurred. So in that case, you'll have to get this 120 rupees value. You can do that later. So this is how uniform tariff rate is being, uniform tariff rate or any other tariff rate is being calculated depending upon the volumetric use, dividing the rate by the volumetric use. So this was about the problems related to the week 12 lectures. like I said in the last class, we'll do some practice problem relating to the earlier week's sessions as a revision for the exam that is going to be coming up soon. So today I have put in some questions from the week 4 and week 5 sessions. Last problem solving session, we have done the second week and third week problems. One second. This is, there's nothing much to understand. They are asking for the, what will be the tariff under a uniform tariff structure per meter cube? What is the amount of money that is going to be there? So we know 120 rupees is the monthly water bill. In 1 month, they are using 15 meter cube of water. So per meter cube, what will be the charges? What is being asked? If you divide 120 divided by 15, you will get 8 meter cube. The other part which I said is they are planning to they're planning to recover this 45 lakhs per month by charging 120 rupees. So you can try multiplying this 50,000 households into 15. That will give you the total consumption. The total consumption into 120 should give 45 lakhs. We can do it also.
Ma'am, but operation and maintenance cost to recover 45 lakh, it will become more. If we will charge rupees 8 per meter cube.
It will be
It will be more if we will charge rupees 8 per meter cube.
more than 45 lakhs will come. Huh?
Yes, ma'am.
Okay, let me just go through this once again, and if I'm getting
I
it, yeah.
I had divided 45 lakh rupees by number of household, and that I got per head 90, and we are consuming 15 meter cube water. So I divided 90 by 15 meter cube. We got rupees 6 per meter cube.
Okay. Let me just go through this problem. If we are not getting the assignment solutions by that time, I'll again clarify it in the next class, or I'll put it in the slide itself. What is the calculation and upload it. I haven't done that part of the calculation. I'll do it and I'll put it in
Okay.
the slide itself. Okay. So we shall go into the week practice sessions for week 4. You can take your time and do these problems. This is definitely going to be useful for the exam preparation that is going to come up. This is based on the week 4 lectures. The first question is, they have given the volume of water in a raw water reservoir with depth 10 meter. 5,000 million liters of water is available in a reservoir of depth 10 meter, and the daily demand daily demand for this amount of water is 30 million liters per day. They have also given the seepage and evaporation loss as 0.85 millimeters per day and 1.75 millimeters per day. You've been asked to compute the annual water losses from the reservoir in million liters. So there you have to calculate the seepage and annual seepage and evaporation losses in million liters. Like I always say, work with the units and try to solve this answer. I'll give you some time. Take your time, think about it, and do the first problem. Then we'll move on to the second problem. First problem, the requirement of daily demand of 30 million liters per day is not coming. We have the volume, we have the depth, we have the seepage and evaporation losses. So based on the volume and the depth, you can find out the area. After finding, you can find out the area, and then you can multiply the evaporation losses and the with the area and multiply it for the annual period to get the annual water losses. So please do that problem. Mujahid, you're right. When I was getting only 6 meter cube, 6 rupees per meter cube if we have to recover the 45 lakh. I don't know why they have given that value. I'll just put it in the discussion forum and clarify that one. Thank you for pointing it out. Okay, so let's move on to the solution for the first problem. So it is 475 million liters. Mujahid, if you're getting the answer, you have to present it in the units that has been asked for. The answer is correct. But units, when you convert it to million liters, it will be divided by 1,000. So here they have given the volume of the reservoir and a depth. From that, we can get the reservoir surface area. Now they have also given the daily water losses, which is 0.85, 1.75. Add it and multiply with this area. You will get the value per day. Now, when you multiply it with 365 days, we will get the annual water losses. Annual water losses, and make sure that you write whatever unit. Even if it is subjective, please mention the units. If it is objective or they're just asking for one value, make sure that you write the answer in the value that they have or the unit that they have requested. Now the second question is to find, assuming that the dead storage of 2 meter for approximately how many days the reservoir would be able to serve the city once completely filled. So if the dead storage is for 2 meters, how much water will be the reservoir able to provide with a demand of 30 million liters per day. So here you will have to use the daily demand of 30 million liters per day. you should also consider that water is being lost through these losses. We have the volume of the water, we have the depth of the total depth of the reservoir. We also have how much depth is being consumed as a dead storage. In dead storage, the water is not being used. So accordingly, compute the number of days, the volume of water, what is the effective storage, that, and from that effective storage, how many number of days can the water be provided to the city is the question that has to be answered over here. Okay, so let's move on. The answer is 128 days. So let's go through the solution together, and maybe you can cross verify where you might have gone wrong. So they have said the dead storage is for 2 meters. So we know we have 5,000 million liters, and we also have found out the surface area. So surface area into 2 meters into 10 to the power minus 3 will give us the million liters of dead storage. So by computing that, we'll get the effective storage of the reservoir, which is 4,000 million liters. So 4,000 million liters is how much water that is going to be provided to the community. Now, rate of water loss also we found it out as 1.3 million liters per day. 475 million liters per year, which is again 1.3 million liters per day. Now, if we say consider the number of days the reservoir can provide water, say number of days is equal to T days, then the effective storage minus water losses in T days is going to be the water that is going to reach the consumers. So we know that 30 million liters per day is the demand. So 30 million liters per day into T days is what is the volume of water the consumers are getting. So 30 into T is the left hand side. In right hand side, we have the effective storage minus the the water losses. We know per day the losses is 1.3. Then for the T days, what will be the loss? It will be 1.3 into T. So totally you will get this equation 30T is equal to 4,000 minus 1.3 T. If you solve this equation, you're going to get 31.3 in the left hand side and 4,000. So T will be equal to 4,000 by 31.3, which is around 127.795 days, which is 128 days. Sangamitra, do you want to see where you went wrong?
Yes, actually, I have not deducted that loss part.
Yes. So that is something that you need to be careful about. That is why they are asking it as a consecutive question, because this might come as a careless mistake to many. So the losses have to be also deducted, and after that only you have to calculate the amount of water that is reaching the consumer end. So let's move on to the next question. Again, a service reservoir is providing effective storage for 150 days. Buffer storage is nothing but effective storage. It is providing it for 150 days for a town with population of 25,000 with the demand of or consumption rate of 135 liters per capita per day. If the effective storage is 75% of the total storage, that is, if this buffer storage is 75% of the total volume, and the maximum permissible depth of 9 meters is maintained, what will be the area of the surface reservoir is the question. So we have the number of days for which a population of 25,000 is provided water at this demand rate. So when you multiply all those values, you're going to get the volume in liters. They have said effective storage is equal to 75% of the total volume. From that, you will get the total volume. Because we have the effective storage in liters, we also have what percentage of volume of the total volume is effective storage, and you will get the total volume from that. Total volume, if you divide by the depth, you will get the area from that. Please do the problem and let me know. You can put in your answers in the chat box. Are you able to do the problem, Sangamitra?
Yes, I think it is option B.
Okay, let's move on to the solution then. Yeah, you're right. It's 7.5 into 10 to the power 4 meters square. Correct. So here again, like I said, we are multiplying the population with the average consumption and the buffer effective storage. We will get the volume of water, that is the effective storage. Then they have said it is 75% of the total volume. So if you divide effective storage by 0.75, we'll get the total volume. Now total volume divided by the depth will give you the surface area. This is a very direct problem. Let's move on to the next question. Now here, for the same data, that is population 25,000, average daily demand 135 LPCD, the water is pumped from 8 a.m. to 11 a.m. That is, the water supply is for 9, 10, 11, 3 hours. First question they have asked is, what is the cumulative daily demand for the city? Cumulative daily demand for the city is what they have asked. So we have been given that out of the total demand from this time to this time, this much is the total demand. If you find out the total demand, we can find out the cumulative daily demand for the city. We've already found out the total demand, so you just need to find the percentages of the total demand and add it all together. You'll get the cumulative daily demand. You can do the second one also. First one is simple calculation. Second one is also simple calculation. Both of them you can do. I think all of this are you able to get it, Sangamitra?
Yes, first two answers I got. Then
Yeah.
next. I have to-
Okay. Okay. So I just wanted to know how would you do this problem when it comes during the exam? I mean, are you supplied with graphical material? Sangamitra, are you there?
Yes, I am here, but
No, will you be
I
provided
don't.
with some graph or something if you're given this problem? When last time when this question is an assignment problem, how were you able to do it?
Uh, no, actually, I have not done using this method. So another method is there, na?
Okay. What is the method that you've used?
That just a minute.
Okay, it's all right. If you're
In,
getting the
no,
answer,
no,
it's fine.
actually, in
Yeah,
tabular form, we have done all the calculations, cumulative
right.
pumping and excess demand, excess supply. Two columns will come if we calculate
Okay,
cumulative
okay, okay.
average hourly demand and cumulative pumping also.
Okay,
Then
okay. Makes sense.
accordingly, I did actually using that
Okay,
method.
okay, okay. Good, good, good. Okay, thank you. Okay, so let's move on to the week 5 practice problems. Again, in this one, a clarifier is given which is 5 meter deep for a water treatment plant that is treating 25 million liters per day of raw water. The volume is 250 meter cube and length to width ratio is 4.5 is to 1. Assuming the density, dynamic viscosity, specific gravity of the particles, we have to calculate the overflow rate. If you remember, the overflow rate is the velocity. You will have to find the settling velocity. When the overflow rate is equal to settling velocity is when settling will happen. So if you find the settling velocity by the terminal velocity of the particles equation, you will be able to find the overflow rate. The formula is the formula name? Yeah, rho g d square, rho g density of water into diameter square of the diameter into acceleration due to gravity into the specific gravity minus 1. So rho into g into s minus 1 d square divided by 18 mu. Mu is the dynamic viscosity. We had studied the condition maximum efficiency of settling is obtained when the overflow rate is equal to the settling velocity of the particle. Settling velocity is given by rho g d square into s minus 1 by 18 mu. If you find that out, you will get the overflow rate. Or you can also find it out by q by a. Sorry. Sorry, the second question is what you have to use the settling velocity for, because we don't have the diameter of the particle. So the first part of the question would be just doing q by a. Second part you will have to equate this overflow rate to the formula what I just now told, and then you will get the diameter. Correct answer. Now, second one, use that formula and find the diameter. Careful of the units, like I always say. Are you able to do the calculations? you're stuck in case of horizontal. I mean, the first question, yes. Second question is directly substitution in the formula, in this formula, rho g d square into s minus 1 by 18 mu. You have to take care of the units because the answer is required in millimeters. So convert it as required. You might be getting it in meter value, so we have to convert it to mm and then write the answer. The third question, they're asking for the horizontal velocity. For that, they have given the length to breadth ratio. So in order to find the horizontal velocity, the area that we have to, q by a is the equation. Instead of a, which is the surface area, we'll have to take the cross-sectional area, which is breadth into depth. So in order to find the breadth value, we use this relation, length is to breadth relation, and find out the breadth value. And using that value, we will find out what the area, cross-sectional area is, which is breadth is 3.33 meters into the height. So length to breadth. Okay, I'm sorry. You'll have to use the length into breadth ratio. Why have they mentioned breadth into height? I don't know. It has to be 5 over here, but they put 4.5.
I think it is right. Horizontal velocity. Actually, the velocity direction is perpendicular to breadth and height.
Yeah.
Horizontal.
So
if it is horizontally flowing, then velocity direction.
cross-sectional area.
To,
So breadth is 3.3 and height has to be measured. No, this one here they have given us the length over here. Height has been given as 5 meters each. So I think instead of 4.5, it has to come 5. So that is how horizontal velocity is calculated. I've taken this answer from the assignment. I'll again go through this once again also. If there's any clarification, I'll edit it over here itself and publish the slides. We also had, yeah, so that was the last question for today. So for next class, we'll be doing the practice session 7 and 8 we've completed. So for 9, 10, 11 and 12 questions related to that. I think 10 and 11, there are no numericals. So we'll solve the numericals for 12th lecture. The 7th lecture where the sludge, the total dissolved solids and permeate and reverse osmosis part and all is coming. So I'll maybe explain this time with the flow diagram. So maybe get prepared on those portions and then we'll contribute the entire session for practice problems in the last session. So thank you for attending today's session. We'll see you in the next week. Thank you, Sangamitra.
Welcome.